Hello students, welcome to a problem solving session on the topic of simple harmonic motion. So in this lecture we are going to solve problem on simple harmonic motion, and I will take problems from previous year's JEE Advance question papers, and we'll solve problems not necessarily in sequential order from previous years, but what we will do is pick up problems randomly and we'll try to solve them. In fact, simple harmonic motion is one of the most important topic in all of physics. It is useful not only for mechanics, but it helps in solving many problems from other topics as well. For example, it is pretty useful in solving problems, in some problems in say related to electromagnetism, then some problems with modern physics and so on. Sometimes concepts are mixed with simple harmonic motion concept, and then you can solve problems utilizing the idea of simple harmonic motion. So let us begin. The first problem that I have taken is a simple one. It's from 2009 JEE. It's in this very simple problem, the displacement time graph of a particle undergoing simple harmonic motion is shown, as you can see from the figure. Kindly please note down the problem. You are asked to find the acceleration of the particle at t is equal to 4 by 3 second. Four options are given, and out of these four options only one option is correct. Okay, so as you can see, information that you have at the moment is what is the displacement or position of the particle at different times. So obviously you need to find out the velocity, and once you know the velocity, then you can find out the acceleration. Now if you notice, you will see that the particle has started from the position x is equal to 0, right? And at time t is equal to 0. So what we will do, I will assume, basically you can assume that the position is represented by this, or displacement is represented by this equation. This is the simple harmonic motion equation. It is how we represent it. A is the amplitude, and omega is the angular frequency of the simple harmonic motion, and phi is the phase. Now, because you know that at time t is equal to 0, x is equal to 0, using this immediately you can find out what is this phase angle phi. Even before that, if you see the diagram carefully, you will see that the amplitude is simply 1. Okay, amplitude is simply equal to 1, and other information that you can find out is the, as I said, phase. So phase, you can just you put down these values there and you will immediately find out phase to be 0, and phi is equal to 0 there. And what other information you can have? If you look at it carefully, the another information that you can have is the time period. From here you see the time period is simply 8 seconds, right? So t is equal to 8 seconds. And if you know t time period, then what other quantities you can find out? Quite clearly, you can find out the angular frequency, and angular frequency is 2 pi by time period. So angular frequency will turn out to be 2 pi by 8, and actually, okay, maybe because of my picture you cannot see it, but it will be pi by 4 per second, right? That would be the angular frequency. So you have a is equal to 1, omega is equal to pi by 4, phi is equal to 0. So your x is equal to simply then sine pi by 4t, right? Yeah, so this is what you have. Now once you have uh, the appropriate form of the uh, displacement and versus time equation with you, Okay, position versus time, you can say that also. Then you can find out what is the velocity. So you differentiate it once to find out the velocity, and that turns out to be pi by 4 cos pi by 4 t. And if you differentiate once again, then you will be able to find out the acceleration at time t. And once you find out the acceleration at time t, at any given time t, so you can immediately find out what is the acceleration at time t is equal to 4 by 3 second, right? And you just, if you put it, it's very simple trivial calculations is going to give you it to be minus root 3 by 32 pi square centimeter per second square. Remember, the position was given in the unit of centimeter. So if you look at the options basically, then one you can immediately see that the correct option should be D. Okay, because D and A look similar, but remember D has this minus sign is there, and there is a minus sign there. So correct option is D. Okay, let us go to another problem. So in this problem, please note it down. In this problem, what is given? A point mass is subject to two simultaneous sinusoidal displacement in x direction. x1 is equal to a sine omega t and x2 is equal to a sine omega t plus 2 pi by 3. Adding a third sinusoidal displacement, x3 is equal to b sine omega t plus phi, brings the mass to complete rest. The value of you are basically asked to find out the value of b and phi. Okay, this question was asked in 2011 JEE. So how to go for it? Again, you see there are four options are given. Out of these four options, only one option is correct. If you look at if you understand the problem, basically what is happening is two forces are actually applied on the point mass particle, and they are applied in such a way that it gives displacement x1 and x2 at the same time at a given time t. And then if you now add another sinusoidal displacement, that is going to that means if you apply another force, which basically is going to result in a displacement, that will lead to the cancellation of all this, and then the particle will come to a halt, complete rest. So let us do this problem. It's very simple one actually. If you see the first that x1 is equal to a sine omega t, and this you can represent in a displacement vector form, because it will be characterized by this amplitude as well as the phase angle. The phase angle here phi is 0, so here I can represent that x1 as a phi is equal to 0. x2 I can you see this phase angle in this case is 2 pi by 3, so it would be represented by the amplitude a, and phi is equal to 2 pi by 3. So this is the phase angle. So, and these two things I can plot in a diagram, vectorial diagram, and this is what I have. And because x1 is directed along this direction and x2 is directed along this direction, there will be resultant direction of these two, and that is x. Okay, shown by this red line. Now the what is said ki you have to add another displacement such that this uh, x actually gets cancelled, and obviously that is going to happen provided you add the displacement in the opposite to this x direction, right, along this vector opposite, and its magnitude should also be the same. So it's very easy. So this is the resultant one, and this can be done simply by you have to, and that is going to have the same amplitude, and the angle phi is what you have to determine. It's very easy. You just have to draw this, extend this in the opposite direction. From the diagram you can see that this angle phi is already, you have this pi by 3 is there, and this angle is pi, so total phi would be this much. It's the angle made by this third vector with this original direction here, that is your x1. So that would be pi plus pi by 3. So pi would turn out to be 4 by 3 into pi. Okay, so amplitude is uh, A again here. So this displacement that you have to add here is simply, it will be characterized by amplitude A and phase angle 4 pi by 3. So if you go for the options there, you can immediately see the correct option would turn out to be what? It would be B, right? It would be, correct option would be simply B. This can be done in another simple another way. You just do it algebraically. This method that I have shown you just now is a vectorial method, graphical method. So you can do it by algebraic method as well. So here you see that you just have to add this third one so that this x1 plus x2, its effects get cancelled out. So x3 is obviously equal to minus of x1 plus x2. Now it becomes a simply trigonometric addition problem here, because x1 is equal to a sin omega t and x2 is equal to a sin omega t plus 2 pi by 3. Now if we apply this sin c plus sin d formula, all of you know it. I think, I'm sure all of you know it. You just apply it there, then what you are going to get is the resultant would turn out to be this one. Now this minus sign is coming outside, so which you can take inside. If you just add a pi there, plus pi there, so this is what you are going to have. So final expression would turn out to be like this. Now x3 is in the original question, it was turned out to be b sin omega t. Now if you compare these two expression, immediately you can see that a is equal to b is equal to a and phi is equal to 4 pi by 3. So the correct option is once again, it's again B. Okay. All right. So this was a very simple problem. Now you can decide which one is the simpler method. Accordingly, you can use it. Okay. Now another problem. It's from 2016, and this problem, yeah, this problem has more than one option correct. Okay, in this particular problem, let me read the problem and you please try to note it down so that it will be easy when I am going to explain it, because I cannot, show this problem again and again in every slide. It will be difficult, so please note it down. Let me read it first. So it says that a block with mass capital M is connected by massless spring with stiffness constant K, okay, to a rigid wall and moves without friction on a horizontal surface. The block oscillates with small amplitude A about an equilibrium position x0. You are asked to consider two cases. Case 1 is when the block is at x0, that is the equilibrium position, and when the block is at x0 plus A. Okay, A is the amplitude. So in both the cases, a particle with mass m, small m, is softly placed on the block, after which they stick to each other. Which of the following statement is or are true about the motion after the mass m is placed on the mass capital M? Okay, what are the options? The options are: the amplitude of oscillation in the first case changes by a factor of this much, that is square root of capital M by small m plus capital M, whereas in the second case it remains unchanged. The final time period of oscillation in both the cases is the same. The total energy decreases in both the cases. The instantaneous speed at x0 of the combined masses decreases in both the cases. I am sure all of you have already noted it down while I actually read this problem. Now to solve this problem, uh, you just see the options. What are the things that is required, that is needed? You have to look for the amplitude in case 1 and case 2, and the time period, total energy, and the instantaneous speed. Okay, let us do this problem. It's a very simple problem. Uh, Initially the situation is this: before case 1 and case 2, this is the situation. The mass block is attached to a spring and of spring constant K, and that spring is attached to a rigid wall here, and x naught is the equilibrium position here. So immediately you can write down what are your angular frequency would be square root of k by m, and time period is obviously t is equal to 2 pi by omega. Okay, and another thing is that amplitude is a, capital A, so therefore the velocity you can write in terms of as omega into a, right? And total energy is equal to half ka square. I think these are familiar results to all of you. So you can utilize this information. So this is the initial situations, okay, initial configuration. Now we are going to consider case 1 and case 2 separately. First, let us consider case 1. In case 1, uh, now what is done, that in case 1, a small mass is put gently on the top of this, softly on this bigger block of mass capital M, because of which what is happening, its velocity simply gets changed to a different one, let us say v1. So once you put that and it gets stick to it, okay, so then your angular frequency would get changed by this much of amount, k divided by m plus capital M plus m. And now in this case linear momentum is conserved, by the way, because there is no external force applied, so linear momentum is conserved. So initially what is the linear momentum? It is simply m into v, right? And now when this is put there, now your new momentum is m plus m into v1, which has to be the same with the initial one. From here you can immediately find out what is v1. Okay, and from this expression it's very easy to see that instantaneous speed, basically it is v1, is smaller than v. Okay, in this case one, v1 is smaller than v. Okay, that one information we obtained. And another one is the new amplitude is a1, so therefore v1 I can write in terms of amplitude as this, omega 1 into a1. Okay, alright, so then a1 you can find out as v1 divided by omega 1, and you already have worked out what is v1. Okay, this using this previous relations we can find out a1 in terms of this initial amplitude in the original thing. So this is what you have, a1 is equal to square root of capital M divided by capital M plus m, and time period is 2 pi by omega 1. Okay, now consider the total energy of the system. Total energy of the system is what? Half k a1 square, right? Here, total energy of the system. So we have found out what is a1. So already we know that half k a square, capital A square, this guy is the energy of the initial system, okay, when the small mass m was not put. So this is the expression we get. Immediately you can see one thing is this, that initial energy is basically getting changed in when I'm considering configuration case 1. Okay, total energy obviously decreases compared to the initial total energy. This is obvious from the equation 4 here. I hope all of you are getting it. So now let us go to case 2. In case 2, this spring is basically, this block is now getting extended to x naught plus a. Okay, x naught was the equilibrium position and now it is given extended. So it is basically getting the extremum position here. So in this position obviously the velocity is going to be 0. Alright, and because of the okay, I'll come to that. And immediately one thing you can see is the uh, angular frequency. I think I just forgot to tell you that, okay, here you are going to put the small mass m here. I forgot to draw it there anyway. So your angular frequency would be root over k by m plus capital M plus small m. Yeah, I have actually written it here. I should have put a mass there. So if a mass m is put over this block, due to conservation of linear momentum, velocity of the combined system just after m is put over m is also 0. Okay, when you have actually, I hope you are getting it, because when it is getting extended, right, extended to the extremum position, you have only the potential energy. So there is no kinetic energy. After that, you actually put this mass. Now, because you are already at the extremum position, velocity is 0. When you put it there, because of conservation of linear momentum, no external force is there. You are putting just gently there without applying any force, without disturbing the system. So therefore, momentum has to get conserved, and velocity of the combined system is going to be 0 again, okay, because of the conservation of linear momentum. Okay, right. So what about the amplitude? It is not going to change. It is going to be the same, right? A2 is equal to A, because you just extended it from the equilibrium position by A. Alright. So immediately you can see the total energy is half k A2 square, which is exactly the same as the initial configuration that we had. That means not case 1, that is when no mass is put on the block. So total energy in this case is not getting changed from the original one in case 2. Okay. As I okay, that is what I have written here. The total energy of the system remains unchanged in case 2. What about the time period? This is 2 pi by omega 2, and omega 2 is equal to omega 1. It's not getting changed. So time period is exactly the same with that of the case 1. Okay. Okay. And yeah, that's what I have written. Clearly, the final time period in both cases is the same. Alright, now let us see the options once again. So if you look at the options carefully, you will find that options, first you see the amplitude of oscillation in the first case changes by a factor of this. Yeah, that is basically the case in case 1, right? We have found that A1 is equal to square root of m, capital M divided by small m plus m into A. Whereas in the second case it remains unchanged. We have seen that A2 is equal to A. Just now we have seen, right? Okay. And what about the time period? Final time period, both the cases are the same. That's also we have seen just now. What about the total energy? Total energy decreases in both the cases? No, it do not decrease in the second case. It remains the same, but in the first case, total energy decreases compared to the initial one. And then instantaneous speed at x0 of the combined mass decreases in both the cases. All right, so yeah, that is correct, right? So options A, B, and D are the ones you have to actually select. These are the correct options. Correct options are A, B, and D. Okay, now let us go to another problem. This was asked in 2009. It's a simple problem, but diagram may look, but it's simple. You see what is, let me read it and you may note it down in the meantime as I read it. A uniform rod of length L, capital L, okay, this rod has length capital L, and mass M is pivoted at the center. Its two ends are attached to two springs of equal spring constants K. Okay, the springs are fixed to rigid supports as shown in the figure, and the rod is free to oscillate in the horizontal plane. The rod is gently pushed through a small angle theta in one direction and released. You are asked to find out the frequency of oscillation. It is basically when you know, gently push it through a small angle, it's going to undergo simple harmonic motion. You just have to get the simple harmonic motion equation, and then thereby you can predict what would be the frequency of it. A simple problem. So options are given, 4 options are given. Out of these 4 options, only one option is correct. This was asked in 2009. Okay, let us see how to do it. So this is the original situation. Now you just give a push to this one. Say if you push it to this direction, and then by a very small angle theta, then because of this, what you are going to have is that both the springs are going to get stressed by how much? Can you make it out? Both the springs will get stressed out by this much of distance, right? So that would be, this is L by 2, this is theta, so this distance is going to be L by 2 sine theta. Okay, L by 2 sine theta, because this theta angle is small, so I can write L by 2 sine theta as L by 2 theta. So if that is so, and this similar is the case with this spring also, so therefore there will be a restoring force on it. The restoring force on the rod by each of the spring would be how much? That would be the spring constant into this, what is this? The stressed amount. So that would be K into L by 2 theta. Okay, so yeah, so this is what I have written. Both the springs get stressed by this much. The restoring force on the rod by each spring is K into L by 2 theta. Okay, so there'd be going to be a torque because there's a rotation of this rod about this point O here, and restoring torque about O is going to be in the anti-clockwise direction, right? It is going to be in the anti-clockwise direction. So this would be how much? This would be simply, this is for one spring, this is for the another spring. This is the force and this is distance. Okay, you know it is a simple trivial thing to work it out. This total torque is, due to this both the springs, will be half KL square theta. So you know the moment of inertia also. Moment of inertia of the rod, of this rod, you know about this oscillation axis would be simply ml square by 12. So this I think everybody knows. This is a very well-known expression for a moment of inertia for a thin rod like this of length L, and the angular acceleration of the rod would be simply, I will write it to be as alpha is equal to d2 theta dt2. Okay, you will not be able to see it, but okay, the theta is the angular displacement. So minus sign is given because it is, I'm writing it minus sign because it is taking, torque is in the anti-clockwise direction. So torque is equal to I into moment of inertia into angular acceleration. So already I have known torque, I have no I know the expression for alpha. If I put everything, okay, I'm putting moment of inertia here, and alpha I'm putting, minus sign I'm taking to the other side, torque expression already I have worked out. So it's very easy to see. If I just do the manipulation, then I will get an equation of this form where omega square would turn out to be 6k divided by m. So once I know omega, so I can immediately find out the frequency. Omega is the angular frequency. What is asked in the problem is the frequency. Okay, so it is omega is equal to 2 pi nu. So we have to find out the nu. So nu is equal to simply this. Okay, so therefore who is the correct option? Option C is the correct one. Okay, it was a simple problem. Now, in this problem, information, this kind of paragraph type questions are very interesting. Because why interesting? Because you can learn many new things. Generally, they are out of, they may not be in your syllabus, but what is asked is very simple kind of concept. Okay, let us read this problem. The phase space diagrams are useful tools in analyzing all kinds of dynamical problems. They are especially useful in studying the changes in motion as initial position and momentum are changed. Here we consider some simple dynamical system in one dimension. For such system, phase space is a plane in which position is plotted along horizontal axis and momentum is plotted along the vertical axis. The phase space diagram is xt versus pet curve. Okay, in this plane. The arrow on the curve indicates time arrow. Okay, this is what we're talking about. Indicates time flow. For example, the phase space diagram for a particle moving with constant velocity is a straight line as shown in the figure. Okay, we use the sign convention in which position or momentum upward or to the right is positive and downward or towards left is negative. So I think all of you are getting it in this example. Uh, this is the phase space diagram, basically phase diagram for a particle moving constant velocity. So if it is moving with constant velocity, momentum is going to be constant at all time. Okay, so that's why it is constant. You see, it started and at all positions. So that's why this diagram will look like this. So simple thing, simple problem, simple idea. It's all about relation between uh, momentum and position. All right. Let us do problems now. What they are asking, there are actually three questions they are asking based on this concept. First question is this: phase space diagram for a ball thrown vertically up from the ground is. So which of these trajectories? There are four options they are giving. So out of these four options, which one is the proper trajectory? Okay, so ball is basically thrown upward, thrown up from the ground. So when it is thrown up from the ground, so obviously it is going to have some, uh, it's up, uh, vertically up from the ground. So how to do it? I think it's what you have to do is find out this kinematic equation all of you know. Suppose the ball is thrown up with some velocity v0 and has a mass m, right? And then you know this equation very trivially equation, v square is equal to in v0, that is the initial velocity minus because it's throwing up there, and from this equation this velocity versus position is there. So you have to simply have to convert it to momentum versus position equation. So you multiply both sides by m square. So if you do that, then what you are going to get is this equation you are going to get, right? You are multiplying all the sides. So now immediately you get a relation between momentum and position. So this is what you get. So plus and p is equal to plus minus square root of m square v0 square, this. Now to uh, get the plot, what you have to do, what is happening at say x is equal to 0, and as the ball is going up, then it is reaching a, you know uh, maximum, then it's again coming down. When it is going to reach the maximum, you know what's going to happen, the ball will instantaneous it will be 0 there, so momentum would be momentarily 0, then it will go down. So it's simple. Okay, so you can analyze it from this equation itself. When the ball goes up, then your momentum is, as you see from here, at x is equal to 0, when the momentum is go up, momentum direction is, you can take plus, so m into v0 is the momentum. All right, and at again when the ball is coming back, the momentum is changing its direction and it is minus mv0. And then at the maximum height, you know that it would be 0, so momentum is simply 0. So these informations are good enough for you to plot the trajectory. Now if you look at these options here, you can see that the correct option is obviously going to be D, because of the fact that at x is equal to 0, momentum when it's going up, you see it's going up here from this position, x is equal to 0 here, the momentum is going up here, it's increasing and it's going to be it's sorry, it's basically here it has some momentum mv0, and it decreases and it becomes 0 at the maximum position, and then it changes its direction, right? And it changes its direction and it becomes minus mv0. So therefore this is what the correct option is. If you look at the other position, immediately you will see and all the positions, all the other plots don't give you the correct this thing. Okay, correct trajectory. So it's trivial problem. I think it's option D is correct. Okay, you can actually immediately by looking at the diagram also you can you know first of all, if you look at diagram A, here the position is shown to be negative, and here you cannot go the bottom of the ground, right? You cannot go below the ground. So therefore you cannot start here. So this option is obviously not correct. Similarly, option A and B immediately you can strike off. Then you can have to think about option C and option D, and then you can again option C also. So I think you get it what I mean to say. All right. So correct option is D, and this one second problem five. This part is of the problem is the phase space diagram of simple harmonic motion is a circle centered at the origin. Please note it down. In the figure, two circles represent the same oscillator, okay, but different initial conditions, and E1 and E2 are the total mechanical energies respectively. Now, when it is said that it is the same oscillator, what does it mean? That means that it has the same, I can say, spring constant, let us say. That means mass and the angular frequency is the same. So it's not really a problem. The energy is simply dependent on the amplitude. So you can, and what is asked is basically the relation between the uh, energies of these two situations. So simply you can apply E is equal to half k a square, which is half m omega square a square. In the first case, E1 is this, amplitude is 2a. So this is half m omega into 2a square, E2 is this. So you just take the ratio, it's very trivial. So E1 it turned out to be 4E2. So I think you know paragraph kind of questions are highly scoring because generally concepts are used to be difficult concepts, but if you read it little bit carefully, I think you will be able to make it out. So I would suggest don't always try to attempt paragraph type of questions. They are not, as you can see from this particular problem, it's a easy problem, and options are given. So correct option would be simply C. All right. So another part is there. Here the spring mass system is given and the mass is submerged in water as shown in the figure. The phase space diagram for one cycle of the system is what? So these are the options given to you. Out of this, which one is the correct one? So quite clearly what is happening is the mass is oscillating simple harmonically. Only thing is that it is put in a water, submerged water. Now, if you look at the diagram, in all the diagrams, you see the position is started. It is starting from a non-zero value of position. So, what we can do, we can assume the position to have an expression like say x is equal to a cos omega t. Now, I just need to find out the momentum. So, I differentiate it once, and then I get the momentum expression. Immediately, I get that this is minus m a omega sine omega t. So if I plot x and momentum here versus time with respect to time, position and momentum, you see as x is increasing with time, you know, as time goes on, as x goes on, the momentum is going in the other direction, uh, in the negative direction. I think this hint is good enough to uh, find out the phase trajectory, because as you will see, another thing is happening is that it is the system is submerged in water, and because of that damping causes continuous reduction in the amplitude. Okay, so now if you look at the diagram carefully, what about this? So option A, All right, so it is starting here, and as it's going, momentum is going increasing, but momentum is showing in a positive, but that is not the case, right? What we had is momentum is in the negative direction. So therefore, this cannot be the correct option. Similarly, option D also cannot be correct. What about option B? Option B, you see, yeah, here position as it is going on, changes with time. Momentum is going in the negative direction. That is correct. And ultimately, what is happening that it is returning back to a different position with a reduced position amplitude basically, right? And which is basically the case because it is submerged in water. So I think option, quite clearly option B is the correct. But what about option C? Here also the similar, but here you see it's coming with an enhanced position, but which cannot be the case because amplitude has to decrease. So quite clearly option B is the correct option. Alright, correct option is B. Okay, this is a nice problem. So now let us work out another one. Here, what is given? A simple pendulum has a time period T1. The point of suspension is now moved upward according to relation y is equal to kt square. K is equal to 1 meter per second square. Here y is the vertical displacement. The time period now becomes T2. The ratio of T1 square. Okay, a simple problem because you see, okay, this was asked in 2005. I hope all of you have noted it down. Okay, so if you see that y is equal to kt square, it immediately gives you velocity would be k twice kt if you differentiate once, and acceleration would be twice k. So that means point of suspension is moving upward with an acceleration a is equal to say 2k, and k is equal to 1 meter per second square, so 2 meter per. Okay, let us do it. So this problem can be easily solved by using the concept of pseudo force. So this is the situation you have originally, right? Now this point of suspension O is moving in the upward. Okay, time period is given. This is the situation. This is the time period. Now the point of suspension moves in the upward direction with this according to this relation. As I said, y is equal to, as given, y is equal to kt square, and acceleration is here 2 meter per second square. So this is basically you have the situation. Now if you go into the frame of reference of this point of suspension basically, then it's very easy to solve this problem by applying this concept of pseudo force. As you will see, uh, okay, so right, the acceleration of the pendulum with respect to the point of suspension is what? It is simply a plus z, right? Because if I go to this frame here to a plus z, that is a is 2, z is 10, so 12 meter per second square. So therefore time period would be L divided by this acceleration. So this is the time period. Original time period was T1 is equal to 2 pi by L by z. So therefore T1 square by T2 square, you immediately, it's very simple problem. This way you can solve it. A plus z by z, so it turns out to be 6 by 5. If you look at the option here, so correct option is obviously A. Okay, you cannot see it because of my picture, but okay, the correct option is A. Alright. Now this is another problem. It's from 1998 JE. So a particle of mass m is executing oscillations about the origin O on the x-axis. Its potential energy is kx mod x cube, where k is a positive constant. If the amplitude of oscillation is a, then what is the time period? So basically it is asking the relation of the time period with its amplitude of oscillation. This is a nice problem, but this problem is exactly, this situation is not simple harmonic, because simple harmonic, the potential is half kx square, and here it is mod kx cube. So obviously this is not a simple harmonic motion, not exactly. but under certain approximation you can always consider it to be simple harmonic. But anyway, if you have this kind of a potential, simple harmonic potential looks like this. And if you on the other hand, here k mod x cube, if you plot it, this would look like this. It is basically wide, you see. And if you from here you can immediately see the total energy when the amplitude is a, it would be simply ka cube. At x is equal to a, u is equal to ka cube, and kinetic energy would be 0 here because this is the extremum here. The total energy would be simply ka cube. Alright, so this much information you have now from here. And then if you look at any point at, suppose at a given position x, between 0 and a, if the velocity is say the potential energy in that case would be u is equal to kx cube, and the velocity is say v, then the kinetic energy would be half mv square. So at any given position x between 0 and a, so total energy according to the total energy would be kx cube plus half mv square. Now because of conservation of energy, this has to be equal to the total energy ka cube. So using this you can find out the what is the velocity, right? Velocity dx dt, you get it. So you want to find out the time period, so you get an equation of this form, and you just have to say okay, I will show you a easy way out. So dx dt you have worked out this way, and then you can find out what is the time period. So you have to just dt, you take it this side, this integral, you can see it, you have to integrate this expression. And because of the symmetry, what I can do, I can just take it from say 0 to a, and it will take the, because of the symmetry, it will take half of the time, t by 2. So 0 to t by 2 dt, and this integration you have to solve. This can be done easily. No, not that easily, but you will see. You just take x is equal to a sine 2 third by theta here, if you put it there. Okay, so what you are going to get, if you put all these things, I think it's this expression you are going to get, and ultimately you will be left out with this expression, but you don't bother about it here, because what is asked is the relation of the time period with the amplitude. So even if you don't solve this integral, it's not going to harm you, because from here you immediately see the time period is dependent as 1 inverse of the square root of the amplitude. So from here you can see that t is directly proportional to 1 by square root of a. In fact, if you can numerically solve it, that is not needed. It would turn out to be 2.1, this integration. So option, if you look at it, the correct option would turn out to be A. Correct option would be A. This problem, this way it looks very, very difficult, but very easily solved if you just apply the dimensional analysis. That's trivially that can be done. So in dimensional analysis, the time period is going to depend on the mass, spring constant is k, okay, the stiffness constant k, and amplitude a. So you know how to do dimensional analysis. So let me say m to the power is raised to the power alpha, this k is raised to beta, and this gamma. And from this expression of energy, potential energy expression, that this energy expression, it has dimension of this much. From here you can find out the dimension of k, and dimension of k, this is energy is m mass into acceleration into distance, right? That way you can make it. So m l squared t to the power minus 2 k l cube. From here you can find out the dimension of k. So that is what is needed here. Amplitude dimension, that the mass dimension is known. So if you put it all these things there, amplitude dimension is obviously turn out to be L. K dimension is this one you have, and now time, this one you can write in dimensional this form you can write. All of you are quite good in dimension analysis, I'm sure. So now you are going to get, you just equate both sides, you are going to get three set of equations. You have to solve it immediately. You can see that beta is equal to minus half and like this. So you are basically bothering about this amplitude part, because what is asked in the question is how time period related to the amplitude. So you better worry about what the value of gamma is. If you find out what is gamma, it would turn out to be minus half. So therefore L to the power minus half. So it obviously, if amplitude is A, then time period is proportional to A to the power minus. So as we have found that very rigorous way, here dimension analysis is giving you in very 2-3 steps you are going to get the answer. Actually it was meant to be done like this only, I suppose. There is no need to go for the rigorous method. Okay, so I think I will stop here. Thank you.